right, this question is a 100% need to know kind of question. Every single thing on here you want to feel awesome about. So stop, pause, rewatch certain parts that you need to watch. And when you're ready, solve this problem. Print out a whole blank copy and do it again. This problem has a little bit of everything with circuits so far. So let's take a look. 4 light bulbs are connected in a circuit with a 24-volt battery with no internal resistance as shown above. All right, or to the right. Determine the average potential energy change of an electron as it moves from point Z to point X. And first of all, a few things I'm noticing there. It makes sense that an electron is going to move from point Z to point X, away from the negative side of the battery toward the positive side of the battery, like being pushed by the electron behind it. And if I'm talking about the average potential energy, I'm talking about delta U. That's always been our symbol for potential energy. And we're going to use delta UE because we're talking about a circuit. And specifically the charge Q that we're talking about is an electron. And I know that as we go from point Z to point X, we're going from a place that has a potential of 0 volts to a place that has a potential of 24 volts. I guess you could say negative 12 to positive 12 to be more precise, but this works too. Either way, what's definitely happening is we're going through a potential difference of plus 24 volts. So simply, this one becomes the fact that what a potential difference is a change in potential energy per unit charge in there. Or if I wanted to rearrange this, I could say Q delta V equals delta UE. And my Q is my electron, negative 1.6 times 10 to the negative 19th coulombs, times a gain of 24 volts, equals a loss of potential energy, or a negative 3.84 times 10 to the negative 18th joules. Energy measured in joules. And as I said before, that negative means something to me. It means that we lose energy. Losing energy makes sense for this electron. And really, I shouldn't say electron. Typo right here. This should say electron battery system. One object can't have potential energy, so it has to be multiple things. I know that this system, though, is definitely losing energy because the bulbs are gaining thermal energy. Energy is leaving the system and turning into heat. Where that thermal energy came from is from the bulbs. Energy came from energy came from the system, the electron battery system. The electron had potential energy with the battery and has less now because it went through these bulbs and the bulbs gained thermal energy. They let off some heat and they let off some light. So that's how that works. We also see that we lost energy because this number was negative, which means something. It's a loss in potential energy for that electron. All right, calculate the equivalent resistance of the circuit. Gotta feel good here. Here are these bulbs, which we are told their resistances. 6 ohms. 3 ohms in parallel connected to a 12 ohm resistor and a 24 ohm resistor in parallel. Okay, so easy. Parallel resistors, I can combine them to make a 2 ohm resistor. 1 over 6 plus 1 over 3 equals 1 over the equivalent resistance. Same thing for this one, giving me an 8 ohm resistor. That simplifies down to a 10 ohm resistor with an 8 and a 2 in series. My equivalent resistance is 10 ohms. Got to be able to do that cold. The magnitude of the current through point Y. Okay, point Y up here appears to be at this branch where bulb B is located, which is the 3 ohm light bulb. I'm just going to find the current in the 3 ohm light bulb because the current here is the same as the current here, which is the same as the current here. The same amount of electrons that walk down this hallway walk down this one. Okay, so to figure this out, let's start down here, knowing that this 10 ohm resistor experiences the full voltage drop of 24 volts. That has to happen because in this loop, you have to go from 24 volts to 0 volts, and you're dropping your potential across these resistors. Since it's 24 volts across the whole circuit, this must be 2.4 amps due to Ohm's law. It's not really a 10 ohm resistor, it's really a 2 and an 8 in series, so both of them experience 2.4 amps. And this one would then experience a potential difference of 4.8 volts and 19.2 volts. Sorry that everything's in purple, but my potential difference is that curved arrow. My current is my straight arrow going straight through. This isn't really a 2 ohm resistor, it's really a 3 and a 6 in parallel, which both experience the same potential difference drop of 4.8 volts. That means the current through this branch ends up being 4.8 volts divided by 3 ohms, or 1.6 amps, and my work is shown above. I would note that if this were a test or a quiz. To see that right there, that all I ended up doing was I equals delta V over R. Do not make the mistake here of using 24 volts as this delta V. We only want the potential difference across this light bulb. We want to know that delta V. That is not the full 24 volts because there is another light bulb to get through. We want to know the current in only bulb B, not bulb A. So we do not want the total current that's going through the battery. Be very careful about that. We want the current in bulb B, so we want to make sure all of these match up with bulb B, which was right next to point Y. Speaking of point Y, indicate on the diagram the direction of the current through point Y. Easy. Current travels from high potential to low potential. That must be this direction, traveling from 24 to 0. How much charge passes by point Y in 1 minute? How much charge? That's a question of delta Q. How much 1 minute? That's a question of time. So I can really use this idea of I, and what current is delta Q over delta T. Or, doing a little algebra, delta Q equals I delta T. Or 1.6 amps, my answer from before, multiplied by 60 seconds, which is just 1 minute in my SI unit of seconds, and I get 96 coulombs. Boom, that makes sense because an amp is a coulomb per second. That works. D, calculate the energy dissipated. What is our change in energy in the 12 ohm bulb? Okay. I can find how much energy is dissipated by looking at the power multiplied by an amount of time. Put a delta T for an amount of time there. The power output of the 12 ohm bulb, I don't know. So I have to go back here and say, okay, this 12 ohm bulb, I look and see it has a 19.2 voltage drop. And there we are. And I've got this 12 ohms right here. That's going to work plenty good. So P, delta V squared over R. You could also use I delta V. You could also use I squared R, whichever one you would like to. I'm going to use delta V squared over R times delta T. I know that that is 19.2 volts. And that's going to be squared over this R, which the resistance of it is 12 ohms, and then 5 seconds. Depending on your calculator rounding, you're going to get an answer around 150 joules. And that's fine. This answer is only going to have two significant figures anyway, so just the 1 and the 5 makes that totally good. Anything around there, you're probably doing the physics right. And then ranking the bulbs in order of brightness, with 1 being the brightest. Cool. This is a question of power. You can look at them individually and say, what is the power of A, what's the power of B, and what is the power of C? But these C and D have such a huge voltage drop compared to the voltage drop in A and B, they're going to be brighter. If power is delta V squared over R, they're going to be much brighter than A and B, with C being the brightest bulb. That's our 1 and that's our 2. D has more resistance right there with the same potential difference, so smaller denominator means more power. And then the same is true for A and B. Same potential difference, but different resistances. So then we're left with bulb A being our weakest bulb, and bulb 3 for bulb B, all by their power rankings. You can find them numerically, but it also helps to be able to think about it conceptually as well. What makes a bright light bulb? Brightness is power. So there we go. Pause anything you need to look through this again, watch it, and ask questions to the people around you, to me, and work until you can do this problem solo. Because if you can do this problem solo, chances are you're going to be able to do your next circuit problem solo as well. Good luck and make it happen.